Alright, so in this video we're going to learn about A to D cards, that is analog to digital cards, which are generally used along with PLC to read analog signals from outside the world. For example, you can see here we have a potentiometer, alright, and potentiometer is basically a variable resistance, which is rated as 5 kilo ohm. Suppose we want to read the signal from this potentiometer, which is connected to a 10 volt power supply. As you can see here, it has three terminals. One is connected to positive 10 volts, another is connected to 0, and this middle terminal will give you 0 to 10 volt when you move this pointer. Alright, that's what potentiometer is, because as we move the resistance, it divides the potential. So here we are going to get 0 to 10 volt. Now this signal we want to read in a PLC. So how to do that? For that we have to install A to D card. Now this symbolizes the terminals of A to D cards, which is written here. Now this card has some specifications. So in this video we're going to see what are the specifications, what does it mean actually. So as you can see here, it specifies that it can read voltage range from -10 to +10 and current range from -20 milliamps to +20 milliamperes. Alright, so in this case we have voltage range 0 to 10 volt. So what will happen if you give a voltage to a card? So now this card has 4 channels. Alright, channel 1, 2, 3, 4. Now in this one channel we have 4 terminals, V plus, I plus, common and FG. V plus is the voltage input, I plus is the current input, C common is the main common of a card, and FG is functional ground. Alright, so the voltage signal will be given to V plus. So we have connected 0 to 10 volt to V plus. Similarly, you can see in my video I have this potentiometer which is connected to my real card. I'll show you the wiring later on. And then we have a common which is connected to 0 volt here. So the potential difference between common and voltage will be read by the PLC, and that will be converted into digital form. That's what's the main purpose of A to D, and that digital conversion will read inside the PLC. Okay, so now there are some specific terms which are related to this card. For example, resolution. Now what is a resolution? Resolution, it says that this card has a 14-bit resolution, and if you calculate 14-bit, that is 2 raised to 14, that will come something around 16,300. So I'm taking a round figure, 16,000 bits. Okay, so the voltage range is -10 to +10, that is a 20 volts range that is converted into 16,000 bits. That is a resolution. So if you calculate the resolution of 1 bit, that comes out to be 1.25 millivolts. So 1 bit represents 1.25 millivolts in this analog card. So if you have a voltage of 0, that will be represented by 0 bits, 10 volt represented by 8 bits. So if you see -10 volt to +10 volt, that will vary from -8,000 to +8,000 bits. So now there is no minus voltage actually. So this minus comes if you rotate this wires, it will show the voltage in minus, or if sensor is giving a minus voltage range, that it can be detected. So the overall range is 0 to 8,000 bits for 0 to 10 volt. Now if you calculate the resolution, 1 bit will be equivalent to 1.25 millivolts. It means the minimum voltage it can sense is 1.25. Now coming to some resolution figures, suppose if your resolution is 10 bit, then with 1 bit it can sense 20 millivolt. That is a minimum signal which your card can measure. So the more resolution you have, the more accuracy, or you can say that the lesser voltage it can read. So my card has 14-bit resolution. Okay, so in channel 2 similarly we have connected a drive. Now if you know something about that, which is coming from AFM. AFM is your analog frequency meter, which gives you frequency feedback in terms of voltage, again 0 to 10 volt. Now you notice that this 0 to 10 volt is a very standardized signals. You may find it in many feedback devices which are giving feedback in terms of voltage, that is 0 to 10. So that's why the range of the card is also from -10 to +10, just to match up these specifications. So this AFM is giving 0 to 10 volts. So we have connected AFM to V plus of second card and ground to common of not second card, but second channel. So similarly, we have 4 channels. So you can connect 4 analog inputs and you can measure that and you can compare that as well. So in terms of VFD, if your frequency is 0, feedback will be 0. So bits will be 0. So in the end, what you will read inside the PLC, that is a 0 bit. So frequency is 12.5 Hertz. Proportional voltage will be 2.5 volts and bits will be 2000 here. And for 25 Hertz, 5 volt VDC and 4000 bits. Similarly, at 50 Hertz, 10 VDC, 8000 bits. So for 1 hertz, it will give you 160 bits. That's some calculation we have done here. For this 1 volt, we have 50 bits. So that's the wiring circuit, how we have to wire our PLC card with the external sources. So it can be 2 more sources in this card. So total is a 4 channels, so we can have 4 analog inputs in this card. The only basic thing is connect the variable voltage to V plus to any channel, and the common is to the common of individual channels. Now if you add 5 volt to this common, now it must be noted that it's not necessary you have to add 0 always. If you are giving 5 volt to this common, and if this VDC is giving 10 volt, then the potential difference is 5 volt. So it will convert the digital form with respect to 5 volt, because it will measure the difference between V plus and common. It will not see that if common is 5 and V plus is 10, then it will convert voltage with respect to 10 volt. No, it will convert only voltage which is potential difference between V plus and common. That's what it does. So that was about analog to digital card, some wiring circuits. So now let me show you some practical how does we have wired this circuit in our card, in our trainer. Now this is the trainer which we are using here. That is my A to D card. This is a PLC over here. Now I hope you can see that. This is a PLC over here, and these are the analog cards. This is A to D and this is D to A. And these are the wires which are connected to the panel over here. These are my terminal blocks, and these are my other terminal blocks. This is a whole panel. This is a PLC relay card. Sorry, the relay card is a PLC, and these cards are connected to some D to A. The second card is D to A. First is A to D. A to D signal is coming to here, over here, right? And D to A signal is coming from there to these terminal blocks. So with these terminal blocks, we have connected some terminals. We have connected some devices. Like the first channel is here, and that is connected to my potentiometer, which you can see here. This is the potentiometer which is connected to first channel. And the second channel is connected to my drive, which you can see over here. The feedback of this drive is coming right from there. It is connected to the second channel over here, and that is connected further to my card. So that is same wiring diagram which we have followed from our diagram. Alright. So now, how to wire the circuit? We have done the wiring. Sorry, how to program the circuit. So now let's see the program. We have to read the potential from our potentiometer. So we know that this potentiometer is connected to channel 1. Okay, so we are going to read the values of this potentiometer in our PLC. So for that, what we have to do, I hope you are familiar with this environment. This is a Delta WPL software. This is my setup, auxiliary setup for extension module. Now instead of writing the code, we are going to use the wizards. So if I press on this one, I'm going to have some wizard in which I can design my code. So now focus on this numbers. This number means if it is at 0, this means that what is the first card which is connected to PLC? My first card with next to PLC is the DVP04AD. So I have to select 0 here. Suppose if my 04AD is connected, not adjacent to PLC but at the second position. In that case, I'll select 1. So this defines the position of your PLC card, whether it is slot 0, slot 1, slot 2, slot 3. So mine is slot 0, just next to PLC, so I'll select this one. So in analog input module, I'll go to setup. Right. Now in setup, we have to focus on 2 things mainly. First is the input mode settings. Right. Now coming back to this diagram, now we have to tell the card what is the input mode. Is it the voltage or is it the current? Right. So for that we have to check our input voltage range, and proportionally we have to program the card. So coming back to this wizard, now here we have 2 instructions, read and write. Now where to use which? So suppose if your card is already programmed in a machine and you just want to read the mode of that analog card, for that we'll go to read register. But here in that case we are going to write the command, because we want our channel 1 to act as voltage input, right? Because we have connected a potentiometer, so we'll go to write register. Now write register, we have some conditions. At what condition this mode should be written? So I'm taking here M1000 because I want that it should be written continuously when the PLC is at running state. So you can put any condition. You can put condition when your switch is on or when your sensor is on, then mode should be changed, right? So this condition defines the modes. Now, what is the first mode? That is -10 to +10, which is a quite favorable in my condition because my potential meter is from 0 to 10. So I can use this mode. And for other inputs also, I think these modes are fine. So I'm not going to change anything, but for information, the second mode is -6 volt to +10 volt, -12 milliampere to 20 milliampere, and -20 milliamperes to +20 milliamperes. So it's up to you how you want the modes as per your input sensors. So my favorable mode is first one, -10 to +10. So selecting the mode, now we have to click add to list. Now this code has been automatically generated as per this wizard. LD1000 is the condition. 2 means we are writing something, and these coded K0, K1, H000, K1. This is what we have done here, setting the value. Now this code is written. Now we want to read the value. For that, we'll go to channel 1 input present value. Here we are going to read it because the external voltage is 0 to 10 volt. We want to read that, so there is no option to write because that is an analog input card. So going to read, again condition, I'm giving the same condition, 1000, and some data register to store the value. So let's take it Z0, add to list, okay. So this is the code which has been generated automatically. Now I'm going to write some comments here. Mode setting. Oops. And here I can write input voltage conversion at channel 1. This is fine. So let me just download this one. So now the voltage has been converted, as you can see here. The 7086, it is a voltage which has been converted. Now if you see my potentiometer, I'm going to rotate that. Now, as I'm rotating it, voltage is decreasing, and that is reflecting in the program. So if I rotate fully, it is showing 0. There is no voltage here. So the moment I rotate it, I'll have proportional values in my data card. Now this data card is converting the value, and PLC is reading from the data card. That is what's happening here. So if I go to here, it means my proportional voltage is right now 5 volts. Because at 5 volt I'm getting 4000 bits, and at 10 volts I'll be getting 8000 bits. This is the conversion of my A to D with respect to potentiometer. Now using that, we can make several logics. For example, I want that if my voltage is above let's say 5 volt, my output should be on. So how to make that logic? So I can write something like this. I'm taking some dummy logic, right? NG greater than D0 K4000 out by 0. There might be a situation when your input card is not reading from potentiometer but from some other device. In that case, you can make your logic as per the requirement. Now here, right now it's below 4000, so visor is off. If I go beyond, the visor is on. And I have made a circuit in such a way that with my Y0, my motor will be running. This is, I already have configured my drive by the wiring circuits, which we will be studying that in later lessons. So above 4 volts, then Y0 my motor is on, and it will remain on up to 10 volts. As if I go below 4 volts, motor will be off. Alright. So similar way you can make some different logics as well. For example, if I want that motor should be on between 4 volts to 8 volts, okay. If the voltage ranges between 4 to 8, we want motor to be running. So what we can do in that case, I can add something here. LD less than D0 K 6000, or let's take 10 volts. We can take 4 to 6 volts as well. So I'm taking 6000. Hold on. So for 8 volt, it will be 6400. Loading the program. Now my range is right now it's to 2500. So going between 4000 to 6400 motor is running. You can see here. And if I go beyond 6400, it will stop because the logic says that. So that is how you can manipulate your analog inputs and can control your outputs accordingly. You can play with this digital bits. By play, I mean you can manipulate the signals in whatever way you want. Okay, you can also have some alarm signal. If your voltage reaches above 8 volts, you can have an alarm here. So above 8 volt, I can have some output here. So I can turn on an output. With Wi-Fi, I can connect my alarm, so which will give me some alarming situation. All right. So above 6400, the motor is off, but Wi-Fi is on. With Wi-Fi, I can actuate anything. So that is up to us. So this is about reading voltages from potentiometer. That is an analog. Which is your analog device. Now next is we have connected our drive to channel 2, V plus and I plus. Alright. So we are going to read the feedback of this drive in the channel 2. So let's continue the program. I'm adding reading voltage feedback from drive. Okay. So let's not have this here. Now drive is at channel 2, so I'll go back here. I'll go to 0, setup. Now I have already done the mode settings, so I just need to go to channel 2, read resistor, condition M1000, and that resistor I'm taking 5. Okay. So now this will read the feedback from the drive. So let me adjust the camera for you so that you can see the exact feedback from the drive. Now one thing you should note that drive should be running, should give feedback only when it is at run state. So right now my drive is at stop mode. It's not running. I need to put some parameter to start this drive because now I want this on off operation from the drive itself. Okay. So for that, let me adjust the setting. Okay, so now my drive is running at 26.7 Hertz. So proportionally, you will find the feedback here. I'm showing 45.06. Now the feedback is not from the commanded frequency. This is the commanded frequency. But feedback will come from the output frequency, which is H26.7. So if I rotate this frequency, if I change the frequency by rotating this pod, you'll have a similar proportional value in the card here, as you can see here. So if I go to 0, it will be 0. Right? This drive is not running at home. If I rotate, the frequency is changing, and similar way your feedback is coming with the drive, the PLC. So if I increase the speed at 50 Hertz, now you can see that this is the rate of acceleration. Similar rate of acceleration is in the PLC card. The drive is running at the maximum speed. We have 8191, which is the maximum digital bits at 10 volts. So we are actually having the voltage, feedback voltage from here, which is going to the card, and that is being converted into digital bits, which are being read by the PLC from the card itself. That is the feedback coming from the drive. Now what you can do is you can again put some alarm. That drive should be between 2 to 20 Hertz to 40 Hertz. Alright, so let's make the program here. Suppose we want that if drive is between 20 to 40 Hertz, then it's a favorable condition. This condition is fine. But if it is below 20 or above 40, you need some alarm situation. So how to get alarm below 20 and above 40? Let's see that. So I'm going to write some comments. Below 20, for that we need to calculate something. So as you can see here, 25 Hertz is 4000. So let's take a dummy figure of 12.5 Hertz. So we want frequency between 12.5 and 37.5, in which our condition is fine. So we'll take 2000 bits and 6000 bits. Okay, we need alarming situation below 2000 and above 6000. So for that, below 2000, I write ND less than D0 K 2000. below 2000 and above 6000, and in this place I can write out y5. Let's say y5 is our amount. Empty greater than d0 6000. Reach online again. Sorry, I have to write d5 now because d0 is for the channel 1. This is d5. So now right now value is between 3000. Let's see that it's 19.6 hertz. So up to 37.5 is where I am. And above that, above 6000. Hold on, I have some mistake in the some logic mistake. I should have connected this in parallel because there are two connections in it. This will come 20. Roll back. 20. Like this. We just upload that. So now, let's go ahead again. Alright, actually Wi-Fi is connected to some multi-speed upload which is having a frequency of 0 Hz. So instead of Wi-Fi, I'm just taking some dummy memory bits, let's say 5. Okay, because Wi-Fi is already connected to multi-speed, which is giving a 0 speed command to my device. Okay. So now, going back here, you can see Wi-Fi started, here you can see the frequency. So if it is below 2000, that is 12.5 Hz, my M5 is on, which can be some alarm situation in your HMI as well. So if I go beyond, you can see that M5 is straight away off at 12.5 or 12. Okay. So now as I go beyond 37.5 Hz, you find output M5 is on. Okay, at this situation. So which is not required. So you can give some alarming situation. So that is how you can read the feedback and you can control that using your some mathematical instructions, compare instructions. You can control the output. You can manipulate the input. That's how you can manipulate the feedbacks of a drive, and you can even display that in your HMI. If you have an HMI, you can put this address D5 into some meter display, and you can do the scaling operation, and you can show the RPM on the HMI screen. That we can also do that. In some live sessions, I can show you how to have this value in an HMI, how to give the feedback in terms of frequency or in terms of RPM or in terms of voltage in your HMI. So that was all about reading the feedbacks from the potentiometer or from the drive and controlling the output accordingly. So even that, you can do some blinking operation of the output beyond some limit. You can blink the output so just to indicate that, and that is all your logical skills. And the PLC card, the main purpose is how to read and how to write the values. This is writing the values, this is reading the values. The rest is it's all your PLC logics, how you can read the feedback and how you can use that feedback in some favorable conditions. Right. So that is all about reading the analog inputs in your analog.